Hi everybody. In this video, I will cover how you find the constraints when you have multiple pulleys and perhaps even moving pulleys. I found the below diagram with all its labels at this webpage, but this is a common problem known as the double Atwood machine. So here we have it. There's a lot going on here, a lot of work I've done for you already. You might want to pause the video and just take it all in. Let me explain the diagram first. So firstly, we have two massless pulleys, as usual. And we have some massless ropes that are taut, and they neither compress nor stretch in order to break, as usual. And then notice, as M3 goes up, pulley A is going down. So pulley A is moving, and at the same time, M2 is moving over pulley A, and M1 is moving also. Pulley B, though, is fixed to the ceiling and not moving. Also notice, unlike with previous examples, we have two ropes here. We have a rope going around pulley B and fixed firmly to pulley A's axle. We could call it rope B, that's length LB. And then we have this rope going around pulley A, which we could call rope A, and it has length LA. They are two separate ropes, which means that not all the tensions are equal to each other anymore, as in previous examples. Finally, I put my origin on the ground and made the up direction positive and to the right positive per the usual convention. Of course, all we are interested in is the y direction because that's the only direction where we have movement acceleration happening. I've drawn the free body diagrams for M1, M2, and M3 and drew their Newton's second law, wrote their Newton's second law equations out as well. All the tensions are positive because I made the up direction positive. And then finally, I did something unusual here, and I wrote a free body diagram for pulley A. This is unusual because we don't usually draw free body diagrams for massless objects, but you will see why this is important soon enough. I'm going to write out its Newton's second law equation as well, but first, let's take care of the tension constraint. So we have two ropes here. In rope B, that's where tension 3 and tension 4 are. So one constraint is that tension 3 and tension 4 are equal. We could call it tension B. And likewise, tension 1 and tension 2 are equal because they're in the same rope. Tension is the same in a rope. So we could call this tension A. So let's go ahead and plug in that constraint into my Newton's second law equations. Tension 1 and 2, they become tension A. Tension 3 becomes tension B. And now I will go ahead and write out that Newton's second law equation for pulley A. We have tension 4 going up, which we saw already was tension B. And then we have tension 1 and tension 2 going down, because remember Newton's third law, right? So the ropes are pulling down on pulley A with tension 2 and tension 1. But tension 2 and tension 1 are equal. They're both tension A, so it's pulling down with 2 times tension A. And then what is this going to be equal to? Well, the pulley is massless, so it has zero mass. So 0 times whatever acceleration pulley A has is 0. And so this whole thing is just 0. So we have the tension constraint. We've written out Newton's second law equation. Now let's get the acceleration constraint. So we're going to get the acceleration constraint in the usual manner. We're going to write position functions for our masses. So you can see y1, y2, and y3, also known as coordinate functions. But also, we're going to have to write out position functions for anything that's moving, as well as potentially position functions for things that aren't moving, so that way we can get the length of the rope in terms of our coordinate functions, y1, y2, and y3, because that's the thing we want a constraint with, 1, 2, and 3. So we've also drawn a coordinate function for pulley A and a coordinate function for pulley B. Of course, YB here is constant. It's not moving, but it's important, as you will see in a moment. All right, so now we can start getting our constraint ready. Let's find the length of rope B, which should be constant, right? Rope B, we have this section of rope right here, and then we have the constant section of rope that goes around the pulley, as we've had before. And then we have this section of rope right here. So let's look at the left first. The rope on the left, if you look real carefully, is just YB minus Y3. Red line minus blue line gives green line. Since they're all in the positive direction, the length of the red line is YB, the length of the blue line is Y3, so YB minus Y3 will give the length of the green line, which is that section of the rope that we're interested in. So let's go ahead and write that out down below. So LB is equal to YB minus Y3. And now we need this part of the rope. So what is that going to be equal to? Well, we can use a similar trick. If we take YB and then subtract YA, we'll be left with this green section of rope that we're interested in. Red line minus blue line will give the green line. Length of the red line is YB. Length of the blue line is YA. We want YB minus YA. And then finally, we have that constant section of the rope that's just wrapping around the pulley. And we can simplify this, combine like terms, and we get 2YB minus Y3 minus YA plus C. Okay, great. How about for rope A? Well, it has a constant length of LA, and we want to find the following sections. We want this length on that side, the constant length around the pulley, we can call it C again, and then this length on that side. All right, so as far as this side, we can do a similar subtraction trick. If we do YA, right, YA, and then we subtract Y2, that'll be the same as red line minus blue line, we'll get the green line. And then similarly, if we take YA and subtract Y1, we'll get the green line on the other side. So all together then, we have YA minus Y2, the green line on the left, and then plus YA minus Y1, the green line on the right, and then plus C for the constant portion that just wraps around the pulley. All right, we can simplify this as we did the other ones, combining like terms. And so you get 2YA, and then minus Y2, minus Y1, plus C. All right, we have our constraint equations. And now, as usual, we can take the time derivatives of both sides twice, and that will give us our acceleration constraints. So remember, when you take your derivatives, anything that's constant goes to 0. So LB over here, even after the first derivative, goes to 0. But of course, derivative of 0 is still 0. And then YB, as you remember, YB was also a constant. It was the distance from the ground to pulley B, which wasn't moving. So this goes to 0, leaving us with just our second derivative of Y3, which is A3, and our second derivative of YA, which is A big A, and then plus C, that's a constant as well. And so from this equation, we see, adding acceleration of pulley A to the other side, acceleration of pulley A is equal to minus the acceleration of pulley B3 of mass 3. All right, so that's that. So now let's get the constraint for LA, rope A. So if we take the time derivative twice, we again get a 0 here. The time derivative twice of YA is 2 acceleration A. Then the second time derivative of Y2 is going to be acceleration of mass 2. Then we get acceleration of mass 1. And then this is just a constant, and so it goes to 0. And so all together then over here, adding A1 and A2 to the other side, we find that acceleration A, or rather 2 times the acceleration A, is equal to A1 plus A2. Or if we divide by 2 on both sides, acceleration of pulley A is equal to 1/2 A1 plus A2. All right, so we have some constraints here, but remember, we're only really interested in A1, A2, and A3. So let's combine our constraint equations together. So that way we just have a relationship between A1, A2, and A3. We can do that because big A big A is equal to minus A3. So we can just plug it in over there, and our resulting constraint will be minus A3 is equal to 1/2 A1 plus A2, or equivalently, we can bring the negative sign over if we want, so we have a nice clean expression for A3 and get A3 is equal to minus 1 half A1 plus A2. All right, so here's our constraint. Let's go plug it into our system. So where do we see A3? I see A3 right here. So instead of A3, we're now going to have minus 1 half A1 plus A2. All right, then at this point, you might wonder, well, wait a minute, what about A1 and A2? Well, all you got to do is count your equations and count your unknowns. So how many unknowns do we have? A1, A2, TA, TB. We have 4 unknowns, which means if we have 4 independent equations, we can solve for all of them, which is great because then we can solve for A1 and A2 just like we wanted to do. And we could also solve for the attentions if we so desired. But what do we have? 1, 2, 3, and 4. We have 4 equations, 4 unknowns, and so we can solve for all of them. That's why writing the free body diagram and Newton's second law for pulley A was important, because if we didn't have this equation, we would have 4 unknowns and 3 equations, and we wouldn't be able to solve the system. So there you have it. That's solving multiple pulleys, moving pulleys, the double Atwood machine.